So today we're going to talk about chapter 9 and 11. The book order doesn't quite align with how I wanted to teach it, but I think this will work out better because we'll talk about Anova and regression, but just simple linear regression this week, and next week we'll talk about multiple regression, which is probably the most important skill in this class that you'll learn. So I'll get started. So we'll start talking a little bit about the design of experiments because it helps with the ANOVA, but let's see. So the design of an experiment often spells success or failure. In the pair comparisons example, our statistician changed roles from passive number gathering and analysis to active participation in the design of the experiment. So in this chapter, we introduce the basic ideas of experimental design while leaving the detailed numerical analysis to your handy statistical software package, which in this class we're using Excel, but in other classes you may end up using programs like SPSS or SAS or R or Python, depends. But most of the stuff that we're getting to now is really going to be better in the more advanced statistical packages, depending on where you plan to apply this kind of knowledge. So the elements of a design are the experimental units and the treatments that are to be assigned to those units. So the objective of any design is to compare the treatments. So the variables, quantitative or qualitative, whose effect on a response variable is of interest are called factors. So just some basic definitions here. You need to know what an experimental unit is, a treatment, and a factor. So for medical trials, the patients are the units and the drugs are the treatments. In the mileage example, the experimental units are taxicabs and the treatments to be compared are two different kinds of gas, gas A and gas B. In agricultural experiment, the experimental units are often plots in a field and the treatments might be application of different wheat varieties or tomatoes, which is probably more common, pesticides or fertilizer. I think generally when we start talking about design of experiments, we talk about, a control group of tomatoes plants in one field and a control group or a treatment group in another field that we actually apply the fertilizer to, and we see, what's the tomato yield between those two plots. Okay, so let's do a quick example of identifying treatments. So a certain HMO is attempting to show the benefits of managed healthcare to an insurance company. The HMO believes that certain types of doctors are more cost-effective than others. One theory is that primary specialty is an important factor in measuring the cost effectiveness of physicians. So to investigate this, the HMO obtained independent random samples of 21 HMO physicians from each of 4 primary specialty groups: general practitioner or general practice, internal medicine, pediatrics, and family physician, and recorded the total per member per month charges for each. So we need to identify the different treatments for this group. So the 4 treatments are the different specialties. So it would be the general practice, internal medicine, pediatrics, and family physician are the 4 treatment groups that we're trying to compare and gather more information about so we can understand, is there any real difference between them? But it's going to lead us to a special kind of test that looks at different groups and comparing them and seeing if that difference is statistically significant. So experimental design ideas are used extensively in industrial process optimization, medicine, and social science. Any experimental design uses 3 basic principles, which are clearly illustrated in our cow example that we're going to talk about. But it says social science, but you'll find that, in some business aspects, experimental design is just not ethically able. But for now, if you get to more advanced statistical classes, we'll talk more about that, especially if you're going to take something like econometrics. Anyhow, so some important factors of experimental design is replication. So the same treatments are assigned to different experimental units. Without replication, it's impossible to assess the natural variability and measurement error. So you need to create a study with replication to make sure you're getting the same answer basically each time you compare these particular groups. Otherwise, it could just be a random error. So when we talk about, when we talk about confidence intervals previously, you could have got that one confidence interval that was outside of the norm of all those other 95% confidence intervals. So that's why replication is important. So local control refers to any method that accounts for and reduces natural variability. So one way is to group similar experimental units into blocks. In the cab example, both gasolines were used in each car, and we say that cab is a block. So it's another kind, random block design is another kind of design. So then we get to randomization. For the essential step in all statistics, treatments must be assigned randomly to experimental units. So for each taxi, we assigned gas to A to Tuesday or Wednesday by flipping a coin. If we hadn't, the results could have been run by differences between Tuesday and Wednesday, such as weather. Now we suppose we want to investigate the effect of 2 brands of tires, as well as 2 gasolines. We have 4 possible treatments, which we can lay out in a 2x2 factorial design. The 2 factors are gas and tire make. So block A would be, gas A and tire A. Block B would be gas B with tire A. Block C would be gas A with tire B. And block D would be gas B with tire B. So we can assign the 4 treatments at random to 4 different days for each cab. All 4 treatments, A, B, C, and D, are repeated within each block by a particular cab. This is called a complete randomized block design. So far, we have assumed that every day of the week is the same, but we can control for this too in the following way. Use only 4 cabs and assign the treatment according to the table at the right. So basically, we stagger the treatments so that on a particular day, all treatment combinations have been made, assuming that each of the taxis are exactly the same. That way, we can also control for day of the week. So a 4x4 table with 4 different elements, each appearing once in every column and row is called a Latin square. It's just more terminology. In this experiment, the 4 days and 4 cabs get all 4 treatments exactly once. So the randomization step picks a single Latin square design at random from a list of all possible 4-way Latin squares. So we just keep introducing randomness. That way we can, kind of control for possible bias. So if 4 units is enough, we can increase the number of experimental units by repeating the experimental design, starting with 8 cars. We can divide them into 2 groups and 4, and then repeat the design with each group. That way we could control for, the cab type. So we promised not to go into the data analysis in detail, but here's roughly how a complex design like this is handled. So experimental designs are analyzed by allocating total variability among different sources. In the cab example, the sources of variability are the cab, the tire make, the gas type, and the day, and of course random error, which is part of all statistical models. So analysis of variance, or Anova for short, partitions the total variation, allocating portions to each source. All right, so analysis of variance, Anova, and regression kind of go hand in hand. So we try to talk about them together so that you can see how they interact. In fact, when you run a regression, an Anova table is part of it, so you can see if the model is even worth looking at. So we'll come to regression, and then we'll kind of scoop back and do an Anova, and then we'll do some more regression. So far, we've done statistics on 1 variable at a time, whether it came from a population of pill takers, pickles, or crash cars, several weeks ago. In this chapter, we'll see how to relate 2 variables given the weights of the 92 students in chapter 2. We ask how they are related to the students' heights. So this is an example of a broad class of important questions, such as, does blood pressure level predict life expectancy? Do SAT scores predict college performance? Does reading statistics books makes you a better person? Probably not. So in math class, you probably learned to see relationships displayed as graphs. Given x, you can predict y. Remember back to the slope-intercept form and all that. Well, we're going to bring that back and kind of apply it and make it a little more useful. But in statistics, things are never so clean. We know, or suppose we know, that height has an influence on weight, but it's not the sole influence. There are also other factors too, like sex, age, body type, and of course, random variation. And data never looks that good. Never perfect, but we try to model it or make some assumptions about it to make it as close to fitting a line as possible, which is the underlying theme of regression. So for this chapter, let's label the weight data as y and the height data as x. Thus we have, these pairs of x and y. So is the height and weight of a student I. So we display those points in a two-dimensional plot called a scatter plot. We talked about scatter plots, I think, earlier in this class. So you can see that, we have this average weight here of 150 and an average height of, what is that, like 68. And then you can see all the different points. And you can see there's kind of a trend. Like you could probably fit a line through that data and get, there'd be some error, but it kind of looks like a line would fit there. Or the data does kind of look linear. But can we predict a student's weight y from his or her height x? So regression analysis. The goal is to fit a straight line to this messy scatter plot. So x is called the independent or predictor variable, some key terms there, and y is the dependent variable or response variable. So the regression or prediction line has the form y equals a plus bx, where, if you remember from elementary school or wherever, y equals mx plus b, but we're going to utilize these terms because that's kind of what they do in statistics. But b is kind of the slope of that line, a would be the intercept, the y-intercept, and of course x and y are the 2 points that we're putting in to develop this line that we're going to fit. So to illustrate the fitting process, let's use a smaller rigid data set with only 9 students' height and weight pairs. So how do we get the best fitting line? I would say the line probably wants to go somewhere through there. And if you try to draw a line going that way, I'd say you're crazy. So the idea is to minimize the total spread of the y values from the line, just as when we define the variance. So we look at all the squared y distances from the line and add them up to get the sum of squared errors. So SSE, sum of squared errors. So where does that come from? It's the error that we are off of from this line. And the goal is to make that error as small as possible, right? So of all of these points, and we know how far away we are from that particular point to the line that we've drawn, and the goal of this, of regression in general, is to minimize the error in our model. And that's kind of what this process is. That's why we call it the sum of the squared error. So an aggregate measure of how much the lines predicted yi or y, or mean yi, differ from the actual values of y. Regression or least squares line is a line with the smallest sum of squared errors. So like I was saying, big sum of squared errors because it's way outside the data. Small sum of squared errors is going to go through the data in the best possible way with the least error. So, not to beat around the bush, we give without proof the regression lines formula. It's messy but computable. So y equals a plus bx, where b is the sum of the differences in the x's and the differences of the y's multiplied by the sum of the differences in the x's squared. And what a equals, by manipulating this, the mean of the y minus b times the mean of the x. So Because some of these expressions will show up again, we abbreviate them. So we have the sum of squared x's, we have the sum of squared y's, and we have the sum of the cross product. So this is kind of all behind the scenes stuff. When you get to this, we're going to use software. So know that it exists. I'm not going to test you on, this level of math or make you calculate it out manually because it's kind of tedious. And in the real world, we would just use a statistical package like SAS or R. So for the rigid data set, this would be the whole computation. Basically, you have to multiply all these out and you get a big table of numbers, but a calculator or a computer will do it for you. So we have values of A and B. So B is 1200 over 240, which equals 5. So we have a slope of 5. And A, calculate out as negative 200. So that is where the intercept would be. This has been shifted, so it's not going to show you. It's going to be like way down here, probably further down. So anyways, we have y equals negative 200 plus 5x. That would be the formula for this line, and that would be the best fitting line between those points. And a note, a regression line always passes through the point of the mean of x and the mean of y. That would be right there. So, example, our first example. A country real estate appraiser wants to develop a statistical model to predict the appraised value of houses in a section of the country called East Meadow. One of the many variables thought to be an important predictor of appraised value is the number of rooms in the house. So kind of interesting because we have like a hopping real estate market. So consequently, the appraiser decided to fit the linear regression model. The expectation of y equals beta 0 plus beta 1x, where y equals the appraised value of the house in thousands of dollars, and x equals the number of rooms. Using data collected for a sample of 74 houses in East Meadow, the following result was obtained. So the beta 0 is the intercept, and the beta 1 is the coefficient for the first x term. This is going to become more important when we get to multiple regression, but you should get comfortable with the Greek symbol beta, because when we add more variables, it'll be beta 2, beta 3, beta 4, etc. But this is kind of more of a standard form of what a regression would look like in a real statistical problem. Anyways, I digress. So the formula we get is y equals 74.80 plus 24.65x. So this would be our y-intercept, and this would be our coefficient for our x value, the number of rooms. So give a practical interpretation of the estimate of the slope of the least squares line. So basically, what we need to know is really just this coefficient. This beta 1 coefficient is telling us a particular factor. So for each room in the house, we multiply it by 24.65, and that'll give us an estimate of the value of that house, the appraised value. So a 0-room house would have a base value of 74.8. So that's how we could interpret the y-intercept. Of course, a 0-room house would not be non-existent, so sometimes the intercept is not really interpretable. But we know that for each room that we add, so if there was 2 rooms, we multiply this, and we would add, 24.65 times 2, and we would add it to that intercept, and then we would know what a 2-room house would be valued at. And you do the same thing for each room you add. So a 10-room house, we would multiply 24.65 times 10, add 74.8, and then we would know what a 10-room house appraised value should be. So that is kind of like the very basics of how you interpret a regression output. All right, so country real estate appraiser wants to develop a statistical model to predict the appraised value of houses in a section of the country. One of the many variables thought to be important, blah, blah, blah. That's what I just said. So the key to this slide is when we're looking at hypothesis testing and using regression, We're really just interested in whether or not the beta 1 value or the slope of that line is equal to 0. So is it a horizontal line, right? If the slope is always 0, it would be perfectly horizontal. And that's what the null hypothesis is saying. So it's saying that basically the variables y and x have nothing to do with each other. They're not correlated. That's what the null hypothesis is saying. And what the alternative, or our research hypothesis, or H1, whichever term we end up using, is saying that the slope is greater than 0. So there's some correlation between that x and y value. And that's how you would set up kind of a hypothesis test using regression. It really comes down to, are these variables even correlated at all? So let's look at example 1. We're going to graph the points and find the regression equation. So let's see. We have 2 columns, x and y. So we must be on this one. I feel like I missed a slide on Anova, but I'll come back to it. Okay, so we have those variables, x and y, in 2 columns. And Excel is actually really cool with this and doing all that math that we saw on previous slides for you. So you should have the data analysis tab, and if you don't, just remember it's down in options, add-ins, Excel add-ins, analysis tool pack. You can check that and hit OK, and this should pop up. But we get data analysis, and what we want to do is run a regression. So your y range, you select the y range. Make sure you put labels on because we have a y label. And then for your x value, we'll select our x. Labels are good. Output range, I put D1. Let's see. And then you hit OK. So I already outputted the results, but that's how you get the results. So when you do that, it should display this value. So some very important factors about interpreting regression coefficients. So the first thing, for simple linear regression, so that's when we have only one x variable, we're going to be interested in this r-squared value. That basically tells us how much variability the model is able, or how much variance we're able to explain using this model. So 87 is pretty good. R-squared values go between 0 and 1, and the closer to 1, the better the model. So 87% has a pretty high r-squared, so it's a pretty good model. We'll come back to multiple r-squared when we get to multiple regression. For this simple model, the only part that's really kind of important is that r-squared. Now, the other important parts of this, we're going to come back to Anova in a second, but you have your F test, which comes from the F distribution that we talked about previously. Like I said, it would come back. And what we really want to know is if this is less than 0.05, it tells us that this model is worth interpreting. So significant F value is important. And then finally, we have our coefficients here. So you have your intercept and your x coefficient. So this would be your beta 0 and beta 1 for terminology. It sets up a hypothesis test for you right here. So this is on the intercept. So beta 0 would be equal to 0 if for the null hypothesis, and the alternative would be that beta 0 is greater than 1. But we don't do a lot of hypothesis testing on the intercept. We're really more interested in our x terms, right? So back to the number of rooms. That's something we can control so that we'd be interested in. And in this event, we were to run a t-test on it using regression, we get a p-value of 0.002, then that's a significant value and it gives us the opportunity to interpret the coefficient for the x value. So if this was number of rooms, we could say that for every increase in one room, we would say that the house cost, or y, should go up by this factor of 0.85. So say that these highlighted from this output, these are the 4 important things to look for when you're running a regression analysis. All right. So another example. A study was performed in which medical researchers tested a new method of typing blood using low-cost paper. The researchers applied blood drops to the paper and recorded the rate of absorption, called blood wicking. The table gives the wicking lengths in millimeters for 6 blood drops, each at a different antibody concentration. So we'll let y equal wicking length and x equal antibody concentration. So in the second, same idea. We have, 6 values, but we want to set up a regression the same way. So running data analysis, regression. So we want to, we have length as one variable that we're interested in. Wait, I think I want it the other way, sorry. So our y value, we have concentration, or we have length. That was right. And then for our x value, our variable of interest is the concentration. So then I would output E1 in this case, make sure I put labels, and then it would generate these results. So once again, that's how you set up the regression. We're interested in, since this is simple regression, first the R squared. So 65% of the variance is explained by our model. Sadly though, I would say this model is not worth interpreting. It's kind of a low R squared anyways, because our significance value for our Anova was not significant enough. So basically we can't interpret the model. If we could, then we would go down and continue looking at these values, our beta coefficient for concentration and its p-value. Its p-value is also just barely outside of 0.05, so we can't really interpret the concentration. So not a particularly good model. So you'd have to either probably want to get more data, would be the best way to glean more information from this particular concept of, the blot test based on concentration. So 6, a sample size of 6 is pretty small. Generally in statistics, we want a sample size of at least 30, but that's just the example we were given. Okay, so Anova. We're going to come back to Anova now, as promised. So now we ask, if this is the best fit, how good is it? That's why I was saying we have to look at that F test to see, is this even worth looking at? So in technical terms, how bad is that slope? This is why Anova and regressions are run together. So as you can imagine, the answer to this question depends on how sloppily the data points are spread out. An example, how big is that sum of squared error relative to the total spread of the data? So a good fit would have a small sum of squared error even compared with the small total spread. Bad fit would be a big sum of squared error relative to a small total spread. So good fit, moderate sum of squared error, but large total spread. So if we have a very spread out data, but we can still make it work. Bad fit would be we have large sum of squared error even compared to large total spread. So let's quantify this by apportioning the variability in y. Refer to the picture at right for guidance. So we have y, the mean of y I equals a plus b xi. That's our line. and thus the predicted weights are determined by this regression line, and we're interested in the error distance from here. So Anova Table, we have several sum of squares that we're interested in. Sum of squared regression, sum of squared error, and total sum of squares. So we have this is how you calculate each of those out. I'm not going to make you do this manually. I had to do it when I took a stat class back a zillion years ago, but it was tedious. So value for the rig data, we have 6,000 for the SSR, 4,426 for the sum of squared error, and 10,426 for the total sum of squares. So it's not obvious that the sum of squared, total sum of squares is equal to those two added, but it really makes sense. Whatever is explained with our regression is in this particular sum of squares. Whatever is left over is what's the error, right? So it should make sense as we go along. So that's manually calculating out each of those values. So SSR measures the total variability due to the regression. An example, predicted values of y. So sum of squared error already met is sum of squared error divided by total sum of squares is a proportion of error relative to total spread. Numerical expression for the slop, or the error. So that comes back to that r squared term I was talking about. So the proportion of the total sum of squares accounted for by the regression is equal to 1 minus the sum of squared error divided by the total sum of squares. And that gives us our r squared value. So r squared of 1 would mean all the dots are on the line. R squared of 0 means we'd have a horizontal line and basically it's very poor, nothing correlates to it. So r squared is always less than 1. The closer it is to 1, the tighter the fit of the curve or the line. R squared of 1 corresponds to a perfect fit. And like it says, you should never get a perfect fit, but generally, we'll talk about this more with multiple regression. The more variables you add, the more variance you can explain, but some of those variables may overlap, but we can keep trying to explain more and more of the model and getting rid of as much of the error term as possible, and that'll keep increasing our r squared. So calculating r squared for the rig data set, we get 6,000 divided by 10,426, or 0.58. So 58% of the variation in weight is explained by height. The other 42% is error, which could be any number of problems, such as basically all the variables that we didn't input in the model, right? Sex, age, and gender, etc. There's plenty of, well, that's partly due to the burrito you ate. Anyhow, okay, alternatively, correlation coefficient is the square root of r squared with the sign of b. So, it's, lowercase r now, and because it's the square root, the sign goes up to the right, and if it's negative, it goes down to the right. So negative r means that x is negatively related to y, right? So we're talking about correlation. It's also called Pearson's r correlation coefficient. So r measures the tightness of fit, as well as saying whether increasing x makes y go up or down. So r equals 1. It goes up in this fashion, equals 0.9. Since it's negative, you can see it kind of goes in this direction. If r equals 0, it just looks like completely random data. R equals 0.7. It kind of looks like a line going that way, but you can see the spread is getting further apart. So now let's be honest. Almost nobody does these calculations by hand anymore. Computer, all the work can be done in one line of code, depending on which statistical package you're using. In fact. Okay, so when you get to running something like SAS or SPSS or R, this is kind of what the regression output will look like. So it will give you the regression equation, So, we had weight and height, right? That was our two variables. We're trying to use height to predict somebody's weight. We have our beta 0 or our y-intercept, and we have our x coefficient. So we have a predictor height. We saw that in the Excel kind of printout when it generates. You'll have your coefficient and you'll have your p-value are the two kind of important things to look at. We have our r-squared value, which tells us how much of the variation as explained by the model, and indicates 43% of it is left to error. Then you have your analysis of variance down here, like I said. Basically tells us, is the model even worth looking at? If you have a p-value here greater than 0.05, the model is really not that good, and you should look at things you can do to make it better. So, Anova hypothesis test. Basically what it's saying is you have all these groups, and the null hypothesis is that the means for all the groups are exactly the same. So looks like we have 4 groups here, so we have the mean of the group 1 is equal to mean of group 2 is equal to mean of group 3 is equal to mean of group 4. And the alternative is always easy. It just says at least 2 treatments means differ. So, and basically for that to be, for the our alternative hypothesis to be true, if any one of these is not the same, then we can reject the null hypothesis. So Anova hypothesis testing is actually kind of easier than setting up a 2-sample hypothesis test, because the hypothesis setup is always the same. So how do we do an Anova? So the data in this table was rolled from an experiment that utilized a completely randomized design, so it fits the assumptions for running the test. So we want to run an Anova to determine if the null hypothesis is that the mean 1 is equal to mean 2 is equal to mean 3. So are these means significantly different or not? So that's on tab 1. So same idea. It's in the data analysis tab. You can run an Anova. Should be at the top. It's a single factor. We're only looking at one factor with 3 treatments. So we can highlight our 3 treatments. We have labels in the first row. We're interested in alpha 0.05, output range here. I've already run it, so this is what we would get. And what is of importance, basically what we want to know is the means of these 3 treatments significantly different? And like I said before, what we're really interested in is this value. Since that value is greater than 0.05, these means are not significantly different. Thus, we would have to accept the null hypothesis. So, quick and easy way, but Anova test is used for comparing the means of different groups, but usually we'll see it more in a regression analysis, since the values are correlated. They both deal with sum of squares. This one is between groups, within groups, and total sum of squares, whereas we saw sum of squared error, sum of squared regression, and total sum of squares. They have correlations between each other, and hence why when we're running a regression, we always also have an Anova, because the Anova tells us, is this model even worth looking at? So I think that is the last slide. Come back.